Okay.
So our next speaker is Tobias, DONNER, and he'll be talking about self-oscillating pump in a topological dissipative atom cavity system.
Thank you very much. And I would like to thank the organizers for the kind invitation. I would like to thank the organizers for setting up this workshop, which I like a lot. So this combination of two different fields, I think it's a very good idea. And when I read what's on the web page, which you see here, and I read what about the fields which should be covered, I was very excited because it's like the outline of my talk. So you see, I would like to show you a dynamical phase transition in a driven dissipative atomic ensemble. I would like to show you how we can make use of that system to create a pumping scheme, which you might know from condensed matter models. And last but not least, I would like to show you how we make use of a superradiant phenomenon to induce or to generate pairs of atoms which are correlated in both spin and momentum. So that's the program. I will not cover the last point. That's the platform which we are using. It's a many-body cavity QED system. So we put a quantum gas into a cavity, and the interaction between those two ingredients give rise to those long-range interactions which we've heard so much about already in this conference. And here's the artistic view of it. Two atoms interact via the exchange of photons in this driven dissipative systems. More technically, we put a rubidium-87 Bose-Einstein condensate into a high-finesse optical cavity. And this cavity is initially empty, but we drive the atoms with a laser field, which is a standing wave, far detuned laser field. So the atoms are not electronically excited. That's the same model which Achim just described, but they act only as scatterers for photons. Now we put a cavity resonance close by to the frequency of this driving laser field, such that photons being scattered off the atoms are preferentially ending up inside the cavity. Now the following process mediates these long-range interactions. We take a photon from the pump, scatter it at a first atom into the cavity, and then back into the pump at a second atom. Those two atoms have interacted with each other via the exchange of this photon, and since this photon is delocalized over the entire cavity mode, this is a global range interaction. The system is open, so some of those photons will also leak out, and this renders the system a driven dissipative system, so you can have the conceptual picture of an interacting driven dissipative system. Now these long-range interactions can be very strong, or we can make them very strong by proper choice of detunings and pump strengths here. And this can force the system to undergo a phase transition, and this is the superradiant phase transition, which indeed can be mapped to the Dicke quantum phase transition. And in our case, it's important to note that this is about coupling not the internal state degrees of freedom of the atom, but the external degrees of freedom of the atoms to the light field. So all this happens due to a competition between potential and kinetic energy, and this is why the single particle Hamiltonian, which I showed to you here, is also describing the coupling of motion to the light field inside the cavity. So you see we have the photon energy, we have the kinetic energy of particles, so that's the curvature of the wave function. We have a pumped lattice, so that's the lattice which we apply for the atoms. If there are photons inside the cavity, if A dagger A is non-zero, we have a cavity potential. And then the most important term is the last one, which is our interaction potential. You see it goes with the product of the pump and the cavity wave vectors. And this gives rise to a checkerboard lattice, which is the interaction, or which is the structure the interaction wants to favor. And this couples here to the coherent field inside the cavity. So you can imagine that this potential arises only if there's a coherent field inside the cavity, which interferes with the pump. And this gives you the according lattice the atoms feel. OK, now kinetic energy versus potential energy. If interaction potential here is winning, then the system undergoes a phase transition from a normal phase where there are no photons inside the cavity to a superradiant phase where the atoms form Bragg planes at which this light field is sketched into the cavity. If I take a cut along the pump direction here, then in the self-ordered phase, you will find this lambda periodic structure, which is the potential the atoms are ordering in, and this gives rise then to constructive interference of the light field. Good. So now have a look at the experiment. This is a top view onto one of our 2 experiments. And you see that we indeed have 2 cavities which cross here. But what's important for this talk is only one cavity. It's angled at an angle of 60 degrees with respect to the transverse pump, which is retroreflected at this point. So that's the picture you should have in mind. That's how the atoms could self-order. And this is an according phase diagram. So whatever is red means that we find photons leaking out of the cavity. So it's direct measurement in real time of the cavity field. What is white means that there are no photons inside the cavity. We can not only take a measure of the light field, but also of the atoms directly. And then we find that in this white region, the system shows only one momentum state. So these are atoms after time of flight. While in the colored region, in the self-ordered region, we have these additional momentum states which correspond to this checkerboard lattice the atoms are acquiring. So this phase diagram is shown as a function of the tuning between pump and cavity and the pump strength. And you see the further you detune, the stronger you have to pump in order to overcome kinetic energy, and the system can then self-order. So this is an experiment which has been done in a different version already in 2010, so what Achim was mentioning to us already, and this is what maps to this decay phase transition. What I would like to show you now are 2 new ingredients, and those both ingredients are important in order to show you this pumping scheme which I wanted to show you. First, I would like to show you how self-organization can happen in repulsive potentials. So until now, everything were attractive potentials. And second, how the system reacts to an imbalanced driving field. So let's take a repulsive potential, a repulsive optical lattice. So we blue detuned the laser with respect to the atomic resonance, which means that the atoms are pushed into the dark of this lattice. Now you can ask whether it's at all possible that this system will self-order, because self-ordering means scattering photons. But if they sit in the dark, they will not scatter photons. So what actually happens is that the atoms are moving to regions of maximum intensity. And then they scatter photons into the cavity, but this cavity field now interferes destructively at the position of the atoms. So it's a bit counterintuitive effect where the atoms are able to shovel their own potential minimum while sitting at the maximum of the light field of the pump. Okay, so let's compare attractive versus repulsive self-organization. You see here the case I've shown to you before. So this is negative detuning between pump and cavity. That's the attractive case. Phase diagram, time of flight images. If I were to look into real space, you would find this checkerboard lattice structure the atoms are acquiring. And this was the potential cut along the pump. For the blue detuned case, the phase diagram looks different. And you see that it actually has a re-entrant phase, such that once the lattice is too deep, the system will stop self-ordering again, and then this destructive interference is not working. If I look at the time of flight images, you see that it's not this nice checkerboard lattice, but it looks like stripes, because only 2 of those momentum peaks are macroscopically occupied. And indeed, this would be the stripe phase of the atoms if you could look into real space here. And if I take a cut along the pump, you see that I get now lambda periodic double wells. So that's the new structure which the atoms are acquiring. Now, the second ingredient I would like to introduce is this imbalanced pump. We send more light from the left than from the right. So if you want to describe it, you have this factor epsilon of less light coming from the other side. Which means if you try to build a standing wave, this is not a perfect standing wave, but it has, well, this part which is compensated between the 2, and then there's an additional running wave below it, such that if the atoms try to hide in the dark, they will not be able, because there's still some light impinging onto them. Okay, this is the phase diagram which we get. And you see it has the typical shape of this blue detuned phase diagram, but in addition we find something which is reminiscent of this red detuned phase diagram. And indeed, if you take a time of flight image, we find that we have this stripe phase in the upper part. And in the lower part, you see that we again find this characteristic momentum peaks of this checkerboard lattice. So the atoms undergo a structural phase transition going from one to the other phase. This can be understood if you look again at the single particle Hamiltonian, where you see this term, which is the same I've shown to you before, giving rise to this lambda periodic double wells. But then if you think of the presence of a running wave, then you can describe it as sum of sine plus cosine, such that you get an additional term in this Hamiltonian which comes with the sign of the pump potential. So it flips this potential, and you see that it gives you this lambda periodic single wells. Very important, you see also that one structure, the stripe, is coupling to the real quadrature of the cavity field, while the checkerboard couples to the imaginary quadrature, so I times A minus A dagger of the cavity field. So by looking at the phase of the cavity field with a heterodyne detector, we can distinguish the two cases. That's shown here. You see color-coded that the phase is doing a jump from 0 to pi over 2, going from one phase into the other. Good. Let's have a look at the phase transition. This is the structural phase transition from stripe to checkerboard. And we can do this by looking at the cavity field. And I show it in two different representations. One is here in this complex plane. So you have the real and the imaginary part of the cavity field. And here I just plot the phase. So that's kind of the angle of this vector. And if I do the experiment, we can look in real time what happens to this phase transition. And then you see that when this border here is crossed, the system jumps by pi over 2 in its phase, and we have these oscillations, these excitations, which damp out. And looking in real space, you would say it deforms from a stripe into a checkerboard, but you also see, if I plot for you this Brion zone, that the center of mass of this wave function is shifted by lambda over 2 while the system undergoes this phase transition. Well, now, this is a driven dissipative system, as I told you, but until now we only made use of the fact that we can read out the photons. So where is the physics changing? And the physics will change once this dissipation rate is on the order of the energy of the photons. So if delta C is on the order of the line width of the cavity. We can choose parameters such that this is fulfilled and then retake this phase diagram, and you see that it qualitatively looks the same, but it looks much more noisy. But it's not noise, it's actually nice physics. So if I take a cut along one of those lines here at a fixed detuning, then you see that the phase is indeed starting at 0 and ends up at n over 2 times pi. So it's 7.5 pi here. But you see that in between there's a monotonic evolution of this phase. And this monotonic evolution means that somehow the phase acquired in the system is constantly evolving until it arrives at this point. So again, we can look in this representation of in a complex plane, and then you see we start here in time equals 0, and then we have this chiral evolution of this phase until it ends up in the imaginary plane. Now, in the beginning, I told you that this lattice which the atoms are feeling is built from the interference of the pump and the cavity field. And now if this cavity field is evolving over time, it means that also this potential, which is this interference potential, will evolve over time. So we can have a look at this, and I can tell you that we can decompose this lattice as a sum of a short lambda over 2 periodic lattice and a long wavelength lambda periodic lattice. And the position of the long wavelength lattice depends on this phase of the cavity field. So if I plot the sum of the two in this animation here, then you see that the potential which the atoms are feeling is actually moving in space. That was the moment where we realized what we have here is something which is connected to topological pumping. So it's a Thouless pump, and there's a nice proposal by Matthias Treuer and co-workers, which says take a lambda over 2 periodic lattice and a lambda periodic lattice and slide the two with respect to each other. This should give rise to topological pumping. These experiments were done in the group of Bloch and Takahashi, and they actually used fermions or a Mott insulator, and this showed that an insulating state can show transport if you apply this kind of pumping scheme. So you have to encircle in a parameter space some singularity, and then the lattice potential, if you load a wave packet here, will transport actually your atoms in space. Good, so that was a good motivation for us to look into this. And we also have this evolution around a singularity, if you want. And the system is constantly deforming from stripe to checkerboard and so on. And each time it does this transition, it will be moved by lambda over 2 in space. So we looked into real space imaging of the atoms, looked at the center of mass of our cloud as a function of this phase evolution, or this phase of the cavity, and saw that we indeed find that there is a displacement of the center of mass, so this is a version of this transport. Something which is different is that we don't apply any time-periodic Hamiltonian. So in this proposal by Matthias Treuer, you had to actually shift one of those lattices with respect to the other. So you use a function generator to generate this. We don't do this. And if you think of Archimedes' screw, you always need some AC perturbation. So somebody needs to turn the handle here in order to have a DC transport of your matter. But the question is, who is turning the handle in our case? And the answer is, it's the dissipation. It's if you write down the Hamiltonian, you have to take into account also this I kappa term here, because photons are lost out of the cavity. This gives a phase shift of the light field inside the cavity, and this induces actually an instability. So if you look at the frequency spectrum, just take the same data stream coming out of the cavity and look at the frequency of the light with the heterodyne detector, you see that once the system goes to this pumping region, we get this additional, we get a frequency shift of the pump light, of the light coming out of the cavity with respect to the light we send onto the atoms. This can be understood also if you think of the eigenvalues of the system. So this is a minimal model where we find that we have two eigenvalues which coalesce in the real parts, and then we have this splitting in the imaginary part. So this is one mode which gets gain, one mode which gets loss, and that's exactly the physics which we observe here. And this can be linked then to non-Hermitian physics of two coupled, dissipatively coupled harmonic oscillators. So if we don't fulfill this full scan here, but stop our scan of parameters in the middle, then we can observe that there's indeed a limit cycle. So the system starts a time evolution where we have this constant pumping in space. Okay, this was one part, and I would like to come to the second part, where I promised you we used the same platform to generate atoms or pairs of atoms which are correlated in spin and momentum. And so the platform is the same. We have atoms inside a cavity. Now we have a running wave field, and we pulse this field only very shortly. So it's a quench. And until now, we didn't make use of the spin degree of freedom of the atoms, but this frequency and the polarization of this pump here is such that interacting with the atoms and the cavity will drive spin-changing Raman transitions in the atoms. Okay, if we apply the pulse and look after this pulse in time of flight in a spin-selective manner, then we find that many of the atoms are still in the initial state MF equals 0, but some atoms were actually shifted to MF equals +1 and others to MF equals -1. Okay, so we try to understand what's going on here, and in this understanding, we realize that this is very much connected to nonlinear photonics, where you have this optical parametric amplification. So you have a nonlinear crystal which you pump with green light, and what you get out is single and idler photons which have then frequency shifted, which are frequency shifted and have the corresponding momenta also, or K vectors. And this is a way how you can generate squeezed light. So this made us interested in this process, and if you look into literature, then there are also other processes with which you can do this in cold atoms, like collisional interactions, or in also with cavities and thermal atoms, or if you drive a BEC strongly and again use the collisions. However, our process is remarkable because it couples both spin and momentum at the same time to this. So this is the microscopic picture. We start with the atoms in MF equals 0. And let's take the first atom, which sits somewhere inside this condensate. And since it's a condensate, it's well, I can't tell you which of the atoms it is. It's in a superposition. And this one atom absorbs a photon from the pump, scatters into the cavity, and by this changes its Zeeman substrate to MF equals +1. Since it is a running wave pump, it gets a kick along the positive Z direction. Now this cavity photon is circling inside the cavity, it's virtually exciting the cavity, and it can be reabsorbed by a second atom, which will then scatter stimulated into the pump and go into the state mf equals -1. So this is given here by energy conservation. And you see that since this, again, is a running wave, this momentum kick will be downwards in negative z direction, such that in this picture, which I've shown you here already, all the +1 atoms will be in positive direction and the -1 atoms will be in negative direction. So that's our process, and we wanted then to analyze how well this pair production works and if these are really pairs. And first thing to do is to change the number of atoms in the pump mode, so in this initial condensate, and you see that we have a superlinear growth of this pair production, which is typical for these parametric amplifiers. Next thing we could look at was the statistics of these pairs. And so we counted how many pairs we are creating in one of those experiments and repeated the experiment many times, so over 200 times. And then we plotted the histogram of a number of pairs. And you see that it follows this Bose-Einstein distribution. So sometimes we get little pairs, sometimes we get many pairs. And this is typical if you have quantum fluctuations which seed this kind of pair production. Last thing we could look at was to look at correlations. And you see in this correlation map that it's very likely that we get atoms in the -1 state if we have atoms in the +1 state, and all the other fields are kind of unoccupied. What we're not able to show yet, at least, is that this is a squeezed state. For this, our detection efficiency is not high enough, but that's, of course, something which we are working on. Well, why is it good to have spin and momentum correlated atoms? It's nice if you want to build an interferometer, where you want to separate your atoms and bring them back together. For interferometer, you also need coherence in the system. And that's something which we could show. So by driving it for different times, you see indeed that we have this coherent oscillations of the different mode populations. And this is a nice ingredient which we want to make use of. So with this, I'm at the end. I presented to you 2 different experiments done in 2 different teams in the group of Tillman-Esslinger. And with this, I'm looking forward to your questions.